Hi everyone. I have decided to create kind of an in-depth video covering limits. Reason for that is because I'm teaching Calc BC now for the fourth time, and my particular student, he happened to have a really good grasp of limits. So in our introductory lesson, we didn't really cover limits in depth as we should. So I decided to make a video just to make sure that everyone will understand limits well enough so that by the time we get to derivatives, you'll have a really good understanding of how they work intuitively, because at the base level, derivatives do build quite a bit on the concept of a limit. So it's really, really important for us to understand how limits work algebraically, graphically, and analytically. So what is a limit exactly? In really simple terms, I like to describe the limit as being function behavior around a particular point. And a limit in general just looks like this. This is the notation we use to describe a limit. We have limit as a variable approaches some value of some function. So let's talk about what this means in context of one of our functions. Let's pick f of x as our first function, the blue one. So let's find the limit of f of x as x approaches 1. So we have limit as x approaches 1 of f of x. So sometimes we can just do a direct substitution. What that means is that we're going to take f of x, we're just going to plug 1 in for x. So in essence, sometimes a limit works really nicely like that. Sometimes all you need to do is a direct substitution. So in order to determine whether or not we can even do a substitution like that, we have to see if f exists at our point. So we're picking 1 for our x value of interest. In order to find the limit, we have to prove that that the function exists when x is 1. We have to prove that f of 1 exists in order for us to do direct substitution with the limit. So let's see if it exists. So f of x would be our blue function. If we plug 1 in for x, we get a y value of 2. Very nice. So because this does exist, because f of 1 is equal to 2, that tells us that the limit as x approaches 1 of our function f of x is also equal to 2. And you might be wondering, why is this important? We had algebra. We know how easy it is just to plug in a point into the function and get an answer. Why on earth do we have to use a limit? It seems unnecessary. The reason why limits are useful is because there are some cases where a function may not exist at a particular point, or it may not exist on a particular interval. For example, let's take a look at g of x. We have x is 1, x is 2, x is 3. What happens if we try to find g of 3? The world explodes. That's what happens. If we plug in 3 for x, we can clearly see that there is no point there. So for g of x, we have continuity on this entire interval except when x is equal to 3. So this is one situation in which we have to use a limit. So because we don't have a point here, the best we can hope for is a description of the behavior that occurs around this point. So the point itself doesn't exist, but what if we travel to the right a little bit? We can tell that this line has a slope, and if we move our way to the right, our function will steadily increase. If we go the other way, if we start at our point and then we move in the other direction, we can see that the line is going to have the same slope on the right side as it does on the left. And we can easily analyze the behavior going on around that point. So if we're only dealing with a blue function that's continuous on the entire interval, a limit isn't necessary. A limit is only truly necessary when we have discontinuity like this. So if you've watched my other calculus video on just a limit on, I think it was just on the different types of continuity in discontinuity, you may be familiar with this already. We call this point discontinuity or removable discontinuity because we're removing just one single point. This is a removable discontinuity. Limits are really, really useful if we want to describe behavior around a point and to describe continuity. So g of 3, this does not exist. We can say d and e for does not exist. We can say u or und for undefined. I think I'm just going to say und because g of 3 clearly is undefined. So the function itself may be undefined when x equals 3, but let's see if we can find a limit. We might be able to still find the limit of g of x this time as x approaches 3. So even if g of 3 is undefined, that doesn't necessarily mean that the limit is undefined. And another thing, for functions we use does not exist or undefined when we're describing just simple functions and simple function values. If we're dealing with a limit, we use more of a specialized vocabulary set. Instead of undefined, we would say the limit doesn't exist. So for a function, we would say this is undefined. For a limit, we would say this does not exist. So we're trying to see if the limit exists. So if we take a look at this first limit we did, the limit as x approaches 1 for our function f of x, this limit is equal to 2. So that's how we say it. This is the way we verbalize this information. We say the limit as x approaches 1 of f of x is equal to 2. The limit has a value of 2. So we're going to hopefully see if we can do the same thing for this bottom limit. We're going to take the limit as x approaches 3 of g of x. So we know that the function itself doesn't exist, but that doesn't mean necessarily that the limit doesn't exist as x approaches 3 of g of x. So we want to think in theoreticals here. We want to think theoretically, if this point did exist, where would it be? So it's pretty easy to see that this is just a basic linear function, and that if the point did exist, we can see pretty clearly that it would just fill the hole. It would be right there. So theoretically, if the point exists, it should be at 3, 2. The problem is it doesn't exist. So the function value itself doesn't exist, but we can see that the limit does exist. So we want to ask ourselves, if x was 3, what would we expect the function value to be? And like I said, if we fill the hole, we can see that we would expect that to have a y value of 2. We can see that this point has coordinates 3 and 2. So sure, g of 3 doesn't exist, but we can see that the limit does exist. The limit is equal to 2 when we plug in 3. So the limit as x approaches 3 of g of x is equal to 2. And I'm sorry if your OCD is going up right now because I'm using red. Mine kind of is. I have a little bit of OCD. It's kind of mild, so I think I'm going to just fix that, make it red, make it black. I apologize for that. So we have g of 3 doesn't exist, but the limit as x approaches 3 of g of x certainly does exist. So that's just a reason why limits are useful. We want to compare, if we're trying to compare this in this, that's the best kind of example I can think of that illustrates why limits are useful and what they do to help. So keep in mind, this is just one kind of discontinuity. Remember that this is either called point discontinuity or removable discontinuity. So what I want to do now is I want to talk about different types of discontinuity, but I want to type this first kind up here. So this function exhibits removable discontinuity. I'm going to write that here. So I'm going to create another set of functions for us to work with. Separate our sections. So we have removable discontinuity. The next kind of discontinuity I want to talk about would be infinite discontinuity. And if you haven't seen my other video where we talk about discontinuity, discontinuity just occurs where there are disruptions in the graph. So for example, if we have just a simple line, if we have f of x is this line, this doesn't have any discontinuity because we can see that no matter what x value we pick between these 2 points, if this is point A, this is point B, we can pick literally any real number between point A and point B, and we'll have a function value. It doesn't matter what value we pick on the x-axis, could be literally anything between A and B. We'll never fail to have a function value. So we would say that this linear function right here between A and B is continuous. There's no discontinuity because the entire thing is continuous. But then think about the one we just saw. I'm going to do my best to redraw it, something like this. Remember that we have this discontinuity. So this is a discontinuity because we can tell that there is no y value that exists at this particular x value right here. And I'm sorry my drawing is really horrible. If you've seen enough of my videos, you've come to expect it by now, but if you're new watching me, then I deeply apologize for that. I'm deeply ashamed. So this is just another kind of discontinuity. Again, if we pick two endpoints, if we pick point A to be the beginning and point B to be the end, we can see clearly that we can pick nearly any x value, literally any x value on this domain almost, that would have a y. There's only just one sole exception. It would be this x value right here. So if we pick anything that's greater than x, it's going to be completely continuous. If we pick anything less than x, it's going to be completely continuous. And did I say that right? I meant to say for anything greater than x, it's going to be continuous, and then anything less than x, it's also going to be continuous. The only problem is x itself is not continuous. If we plug in x, we get an undefined function value. So that's how we know that this is discontinuous. That's how we know that we do not have continuity on the entire interval. So that's just a quick crash course on continuity and discontinuity. So back to the problem at hand, back to this new type of limit, new type of discontinuity that we're learning, infinite discontinuity. So infinite discontinuity occurs whenever we have a vertical or horizontal asymptote. So I want to create just another kind of function for this. Let's say we have g of x is equal to 1 over x minus 3. So in order for us to completely understand this new type of discontinuity, I want to graph the function to help us get a better understanding of the discontinuity of the function. So we're going to have x is 1, x is 2, x is 3 is right here. And what we're going to do is we know that the parent function, which is just 1 over x, has a vertical asymptote at x equals 0. But we can see with this new function we have right here that our asymptote is not going to quite be x equals 0. We're going to move the asymptote 3 units to the right. And that's why the asymptote occurs when x is 3 and not when x is 2. So this right here is our vertical asymptote, our VA for short. So let's graph the function. It's going to look something like this. So there are certain values of x that work really, really well. What if we wanted to find the limit as x approaches 4? And then I'm going to get rid of, sorry, I mix up my notation sometime. We already have an f. We already have a g. I'm going to call this actually h of x. So we're going to find the limit as x approaches 4 of h of x. Is it possible? So let's do a direct substitution and find out. So one way we could find out is just substituting 4 in for x. If we substitute 4 in for x, we get 1 over 1, which is just 1. But there is another way to do it. We can also do it graphically. So let's see if we plug in 4 for x, we get a real function value. And it looks like we do. And I know this doesn't look anywhere near y is equal to 1, and I apologize for that. That's just because I have very poor drawing skills and even worse planning, it seems. So the function definitely exists when x is equal to 4. It tells us that h of 4 exists. So because the substitution exists, because we get 1 theoretically when we plug it into the function, get rid of that, we can see that the limit is also certainly going to exist just because we can do a direct substitution and we get 1. But let's try something a little bit different. What if we wanted the limit of h of x as x approaches 3? So let's try a direct substitution. So what happens if we take h of x and we plug in 3 for x? We get h of 3 is equal to 1 divided by 3 minus 3. We get 0 in the denominator. We cannot have that. That is illegal. We're going to get thrown in jail in math land for putting a 0 in the denominator of any fraction. We can't have that. So that's how we know that we can't do a direct substitution. Let's see what happens graphically if we try to plug in 3. Uh-oh, that takes us to our vertical asymptote from before. And it is impossible for a function value to exist along an asymptote. So h of 3 does not exist. H of 3 is undefined. So remember that just because the function value doesn't exist doesn't necessarily mean that the limit of that value doesn't exist. So let's see if we can maybe trace the graph, kind of like what we did before when we had just a removable discontinuity. We could see that if we travel from the right and if we travel from the left, we would expect them to reach the same exact point. So that's how we knew that this limit exists. But how the heck do we know if a limit exists under these circumstances where there's an asymptote? So we want to do something similar to what we did before. We want to trace the graph starting from the right side and working our way to the left. So if we start right here and we travel left, we can see that our function is just going to continue to increase as we travel to the left. All right, now let's see what happens if we do the same thing except we travel from the left side this time. So if we start from the left and we make our way to the right, we travel to the right, we can see that the opposite is happening. We can see that y is not going to increase, y is actually decreasing this time. So that means the limit does not exist. This limit does not exist because if we travel from the right, we get a different value than we would if we travel from the left. That means the limit does not exist, but we can make some kind of an algebraic modification in order to make this limit exist. So we want to think of this in terms of a piecewise function, We want to split this up into two distinct limits, one approaching from one direction and then one approaching from the opposite direction. So instead of just doing x approaching 3 all in one go, we're going to make one very special limit that describes what happens as we start from the left and work our way to the right. So we're still approaching the same value, we're still approaching 3, but we're approaching from the negative side of the graph. So we're going to put this little negative sign right there. We call this a two-sided limit because we can see that we have two sides, one approaching from the left, and then the other side would be approaching from the right. This is a two-sided limit. So we're breaking up a limit into two separate two-sided limits. Or I guess this would be a one-sided limit. Each of these, when we join them together, they make up a two-sided limit. But whoops, sorry about that. This alone is a one-sided limit. We need two one-sided limits to adequately describe function behavior in a situation like this one. So we want to ask ourselves, what happens if we start in the negative side and move our way to the right of h of x? We're going to keep the same function, h of x from before. So if we start from the left and work our way to the right, that's all this means. The way we read this, this would be the limit as x approaches 3 from the left of h of x, or another way of reading that would be the limit as x approaches 3 from below of h of x. So those are both acceptable descriptions of this limit. So let's see what happens if we start at the left side and travel to the right. Let's see what happens to our function as x travels right. So we're going to start here. We're going to move our way to the right. We can see that our function decreases, definitely. So we can say that because our function just decreases on and on forever without bound, the limit of this function as x starts from the left and travels to the right would be negative infinity. Just shoots down to negative infinity. Likewise, let's see what happens if x approach the same value, x approaches 3 from the other direction. So let's read this one out. This says the limit as x approaches 3 from the positive side of h of x, or we could also say it says the limit as x approaches 3 from above of h of x. They mean the same thing. So let's see what happens if we start from the positive side of things and we work our way to the left towards the negatives. So we're going to start right here. We're going to move our way to the right and analyze our function behavior as x approaches 0, or as x just decreases. We can see that our function is going to increase this time. Last time it decreased, it went down to negative infinity. This time it increases, it tends to positive infinity. So the limit as x approaches 3 from above of h of x is just positive infinity. So we have one single limit that doesn't exist, but we're able to make a modification. We split it up into two one-sided limits. Each of them work. So that's how we kind of be strategic in handling a limit like this where we have function behavior traveling in two different directions. We always want to make two one-sided limits for a situation like this one. And then there is one more type of discontinuity I want to talk about today. This would be something called jump discontinuity. So we want to create a function that would best exhibit this type of behavior, that would best exhibit this type of discontinuity. So this mainly applies to piecewise functions. Let's say we have something like this, and we have f, we have g, we have h. I hate going into the j, but I'm going to do it anyway. It kind of makes sense, though, because j stands for jump. So j of x would be our new function. It just sounds really weird even saying j of x, because usually we stop at h. It feels weird even saying j of x. So I'm just going to come up with some generic piecewise function. Let's say we have j of x is equal to x squared, but only when x is less than 2. And then let's say that x is equal to, no, let's say that y is equal to maybe just 1. Say our function value, j of x is 1, only when x is greater than or equal to 2. So let's go ahead and sketch this real quick. A graph will help us really understand this third type of discontinuity. So I'm going to draw x squared like I normally would, but this time I'm going to stop when we get to 2, because we know the function only exists with this function definition when x is strictly less than 2. So what happens if we plug in 2 for x? If we plug in 2 for x, we get 4. And because that doesn't exist in this top function, we're going to put an open circle right there just to indicate that for the top function, we have 2 functions, and for the top one, it does not exist when x is 2. And that's why we put an open circle instead of a closed circle. So x squared would look something kind of like this. That was really bad, but you get the gist. And then I want to sketch the other part of the function now. We know that our function value is going to be 1 whenever x is greater than or equal to 2. So we're going to start with 2. We're going to plug in the point 2, 1. Because x equals 2 is not part of the top function, it's only part of the bottom one. So that's how we know this time it'll be a closed circle and not an open circle, because 2 is part of the domain only for the bottom of the 2 functions. So if we plug in 2, we get 1. If we plug in 3 for the bottom function, we get 1. If we plug in any value at all into the bottom function, we're always going to get 1. So that means it's going to look just like this. So this is our piecewise function, and this exhibits what we call jump discontinuity, because we can see that not only is it a discontinuous function, but there is a considerable gap between known endpoints. So that's pretty much it for jump discontinuity. It's something that occurs whenever there is a measurable distance between 2 or more parts of a piecewise function. And these don't get used very much in calculus. Mainly calculus deals with infinite discontinuity. This is the main type that we're going to be studying in this class, but it's also a really, really good idea to understand jump discontinuity. And before we wrap up this video, I want to talk about limits in terms of jump discontinuity. For example, what happens if we want to find the limit as x approaches 2 of j of x? So a direct substitution doesn't work if we look at the graph. Or does it? Maybe it does. Let's see what happens if we plug in 2. So if we plug in 2, we want to go to the place where there's a closed circle. There's a closed circle right here at the point 2, 1. So that tells us that the limit as x approaches 2 of j of x is equal to 1. But what if we wanted to do a two-sided limit? Is that possible? What if instead of this being the limit as x approaches 2, what if we wanted to make it the limit as x approaches 2 from the left side, from the right side, I mean, or from above? So we're going to start over here at the right. We're going to travel to the left and see what value y approaches as x approaches 2. We can see it's still going to approach 1. So we're still in good shape. This is still going to be 1, even when we add this plus sign right there. The limit as x approaches 2 of j of x is still going to be 1. So I'm going to make another one-sided limit for this. We're going to have x, the limit as x approaches 2, this time from below, of the same function of j of x. Let's see what happens. So we're going to start at our lowest value of x, the origin. We're going to work our way to the right, and we're going to ask ourselves, what would we expect the value of the blue function to be if we were to get all the way up here to the point? Well, sure, the point is open. It's an open circle. We don't technically have a point right there, but the limit definitely does exist. We can tell that theoretically, if a point did exist, it would be right here at y equals 4. So the limit going from below, limit as x approaches 2 from below, excuse me, of j of x, we can see would be 4. So that's how two-sided limits work with jump discontinuity. And I want to go over maybe some more limit solving tools to help us out. Let's say we're dealing with limits algebraically only. Let's say we do not have a graph to help us. Suppose you're taking a test at school and you have not much time left and you just really don't have enough time to graph this. We're given the limit as x approaches 1 of the function x minus 1 divided by x squared minus 1. So remember that job 1, when we're given a new limit, is always just try a direct substitution, see if it'll work. So what happens if we plug in 1 for both of our x values? So on top, we're going to get 1 minus 1, which is 0. On the bottom, we're also going to get 1 minus 1, which is 0. We're going to get 0 over 0. And in calculus, this is something we call an indeterminate limit. I don't even know if I'm spelling that right, but you get the idea. It's a limit where we have certain circumstances that exhibit behavior that would indicate that it doesn't exist at a particular point. This would suggest that the limit does not exist, but it actually does, and we're going to have to do a little bit of algebraic witchcraft to determine the value of this limit when x approaches 1. So if we do a direct substitution, we get an indeterminate limit. So what I actually want to do is I see in the denominator we have some kind of a difference of squares going on here. So let's go ahead and employ difference of squares factoring for this. Difference of squares factoring works like this. We're going to take the square root of the first term, which is just going to be x, minus the square root of the second term, which is just 1, times the square root of the first term plus the square root of the second term. And then this is really useful because we can see that we have an x minus 1 on top, yoink, and an x minus 1 on the bottom, yoink. So we're left with just a simple 1 divided by x plus 1. So now we can definitely do a direct substitution. If we plug in a 1 for x, our denominator becomes 2. So the limit as x approaches 1 of this function is 1/2 because we have 1 over 2 when we plug in x. So the limit has a value of 1/2. So let's try another type of limit problem. Let's try a limit at infinity. Suppose we want to find the limit as x approaches infinity. Maybe we'll just do x. So we know that this is just a direct substitution. Excuse me. It's a direct substitution problem. If we plug in infinity for x, we just get infinity. And this is another type of the thing that we call an indeterminate limit. We get something involving a 0 over 0 or an infinity over infinity because this limit resolves to infinity. We say it does not exist. It does not have a finite value. So this does not exist because the limit value is infinity. Every time we have a limit that has infinity as its answer, we say that the limit does not exist. Let's try something else though. let's try the limit as x approaches infinity of e to the negative x. And I want to show you a third way of doing this. So we've done a limit graphically. We've learned how to solve limits graphically. We've learned how to solve limits algebraically. Let's get into the third commonly used method to evaluate a limit analytically. So analytically, evaluating a limit involves a table like this. We're going to have an x column. We're going to have a y column. And then we're going to take larger and larger and larger values of x and then see what kind of behavior y exhibits when that happens. And mainly, that's just what a limit does anyway. It tells us that we're taking x to infinity. We're going to take bigger and bigger and bigger values of x. So we may want to just start with 0 because we know that we're tending to infinity. We have to just pick larger and larger values of x. So maybe we could try 0 and then 1, and then maybe 10, and then we could do 100, and then 1,000. My OCD is flaring up right now. My own crappy handwriting is making my OCD even worse. This is 1,000. So we might have enough information right now to evaluate this limit. Let's find out. So what we're going to do in the analytic method of evaluating a limit is plugging in all of these values for x and see what kind of behavior y shows as x gets larger and larger. So let's plug in x equals 0 into our function. So we're going to get e to the negative 0, which is just e to the 0, which is just 1. So if we plug in a negative 1, we get e to the negative 1, which is going to just be 1 over e. And then let's see what value that has real quick. So e to the negative 1, if we round to the nearest hundredth place, we're going to have 0.37. Let's see what happens if we plug in 10 for x. We're going to get e to the negative 10th power. And just like with the last one, we're going to round that to the nearest hundredths place. We're going to get 0.000. We're going to get a really, really small number. So I think I might actually give us a few more decimal places. This is going to be approximately 0.0000454. And then maybe we'll just do one more. Maybe we won't do the 1,000. So let's plug in 100 for x and see approximately what function value we get. This is a mind-bogglingly small number. Even Wolfram Alpha is diving into the scientific notation for this one. Wolfram Alpha gets us this 3.72 times 10 to the negative 44 power, which means that we're getting smaller and smaller and smaller. Y is getting closer and closer and closer to 0. So we're using the table method. We used bigger values of x. We just kept picking bigger and bigger values of x every time. And we can see as we're doing that, y would get closer and closer and closer to 0. Y would approach 0 as x approaches infinity. So theoretically, if x could reach infinity, theoretically, y would also reach 0. So the limit as x approaches infinity of e to the negative x is equal to 0. And then there is just one more limit tool we have, but I'm not going to get into it this class because it actually depends on derivatives. So that is all I wanted to cover today as far as the basics on limits. Hope this cleared things up quite a bit for you. Hope this has been helpful. And I will see you in the next video. Goodbye.